episode of the Funtastic Academy. Today we'll be coming back from where last episode left off in a Diwali special, as we continue looking into how your computer's memory sticks of DRAM function, allowing your computer to store huge amounts of data when you're running complex software or playing a video game. But before we get into that, let's answer last episode's quiz question. What is the current generation of DRAM? DDR what? The answer is DDR5. There have been 4 previous generations of DRAM, each limited by higher required input voltages and slower speeds. DDR5 is the most latest up-to-date version of computer memory. Now, let's dive in to see how computers read, write and refresh huge amounts of data. So if you remember from the last video, you can see that this is what a single cell of DRAM looks like. This trench capacitor can store a 1 or 0 via electric charge in the capacitor, and it should be connected to the rest of the system using this bitline wire. You can turn on and off this connection using the word line wire. Let's imagine the word line wire is turned on. Then what happens? If the capacitor has a 0 in it, then whatever is in this bitline wire will go down because it's putting charge into the capacitor. The voltage in the wire will go down if the capacitor is storing a 0. On the other hand, if it's storing a 1, the voltage will go up. So if you stored an in-between value of voltage in between this wire, let's say 0.5 volts, then if you had a 0 in the capacitor, the voltage will decrease, and if you had a 1, it would increase. But that would overwrite the value that we are storing in this capacitor, so it wouldn't be useful. And plus, this capacitor will leak value into the bitline anyway. So we're going to have to constantly refresh the capacitor to keep its value. We'll talk about how to do that in a few minutes. Now, this is the full structure of the DRAM grid array. Now, let's explore the 3 main concepts that DRAM grids can do. That is, reading, writing, and refreshing by putting voltage onto these bit lines and word lines. So, let's explore. To read, what we do is pre-charge all these wires to 0.5 volts and then open a given row by turning on that word line and setting all the other word lines to 0. Now, if there's a 0 in a given cell on the word line we want to read, then it will decrease the voltage of that wire by a tiny amount. We just covered this. But the sense amplifiers will notice that tiny decrease and drive that wire all the way down to 0. That's the job of the amplifiers. This will also make sure that the current doesn't leak slowly over time, because if there was a 0 in that capacitor, it would get driven all the way down to 0 again, making sure there's no data loss. Thus, we can get a 0 as an output. If there's a 1 in that word line, the same logic applies. The wire voltage increases by a tiny amount and the sense amplifier drives it all the way to a 1. Thus, we can get the required voltage outputs from all the bit lines in our given word line. We can then select the specific bit lines that you want to read and output it. To refresh the information, it's a simpler, very similar operation. You just open each of the rows one at a time. Like I said, when we open a row, the sense amplifier makes sure there's no data loss. Let's say there was a 1 in a particular capacitor, but it's decayed to a 0.8. When we put the 0.5s on the wires and then open a row, the voltage on that wire will increase to a tiny amount. The sense amplifier will drive it all the way up to 1, meaning the 0.8 that wasn't a capacitor will turn into a 1. This refreshing capacity is why DRAM is called dynamic. You need power for it to continue storing information. This is different from drives, which physically store the data in magnetic arrays. So any data on your SSD remains even after your device is shut down. But with DRAM, you need to continuously refresh the data to make sure that it stays up to date. Now, for writing information, what you do is you do the same operations for reading, and then you simply take the word lines, the bit lines that you want to write, and then put the current on them. If you want to write 1 to this particular bit line on this word line, you just put a 1 on it using the write drivers. The write drivers do the same thing as the sense amplifiers, but much more powerful. So as soon as there's a tiny 1 on this wire, the write wire will force this capacitor to be 1. You can force all the data in this grid to be whatever you want by simply driving the data on the required bit lines. Now, we've learned how DRAM uses the three proper components of reading, writing, and refreshing memory data. So now, let's cover a few optimizations which make it more advanced than the simple layout we're using and make DRAM a practical, faster storage medium. The first optimization that we're going to cover is row hits. See, opening a row is a complicated process. You need to pre-charge all of these bit lines to 0.5 volts and then choose all the other word lines to 0, except the word line you want to open. That row you set to 1. This takes a long time, and when your program needs to open many different rows in quick succession, that time quickly adds up. So the solution is row hits. It's a software level optimization that aims to get consecutive uses of the data on the same row. This way, if the DRAM sees that you're accessing the same row as you did last clock cycle, it doesn't need to open a new row, saving time. So many of your programs that you're running are designed to get data from the same row as quickly as possible. The opposite to this is trashing, the term used for when you need to quickly open different rows in succession, which results in a huge loss of time. The second optimization we're going to cover is the burst buffer. The idea is that it might take a long time to get the particular bit lines you want. When you open a row for reading, all the bit lines, which you know is a massive array, way more than 5, a massive array of bit lines is directly connected to the multiplexer, but you can only get 8 of those at a time. The burst buffer optimization basically allows you to quickly cycle between a burst of, let's say, around 100 bits of memory. You can quickly cycle through those in 16 clock cycles or so and get huge quick access to any particular block of memory. Burst buffer optimization allows you to quickly transfer data as an intermediary between the DRAM and the CPU. And those are the two most important optimizations in modern DRAM. And that concludes this Diwali special video on DRAM. To summarize, today we looked into how DRAMs open rows and use sense amplifiers to read, write, and refresh the data they store. We also looked into two optimizations that they use, the burst buffer and row hits, allowing them to be even faster for your computer's use. Now, before we leave this video, let's end with a simple quiz question. What is the equivalent of DRAM used by your graphics card or GPU instead of your CPU? Tell me the answer and I'll see you in the next episode of Funtastic Academy. Bye!